So next, let's move on to two-dimensional dynamic programming, and let's solve a pretty familiar problem at this point, counting paths. So we're going to be given a two-dimensional grid, and we're starting at the top left. We want to go to the bottom right, and we want to count the number of paths that can lead us there. Now, in this case, though, there aren't any blockers. Like before, we had zeros and ones. Ones were blockers, but this time we don't have that. And we have another thing that's going to simplify things for us. We can only move down or move to the right. So that's going to make things pretty easy for us. So for example, one path would look like this. Another path would look like that. Since we can only move down or to the right, every path is actually going to be the exact same length, because as we move down, we're getting closer to the bottom right. As we move to the right, we're getting closer to the bottom right. And, eventually the paths are going to converge and they're both going to be the same length. Every single path to the result is going to be the same length. Now, based on what we learned in the graph section, we can do this recursively with depth first search. And so that's the brute force way to do this, but it's not going to be very efficient. So suppose we're given the number of rows and the number of columns. In this case, notice we actually don't care about the grid itself. It's not a parameter. What we actually care about are the dimensions of the grid. In this case, it's a square grid, so it's 4 by 4. So 4 rows and 4 columns, and the input is going to be the starting position. We know it's going to be 0, 0 to start with. So when I'm actually calling brute force, I'm passing in 0, 0 as the starting coordinates, and the dimensions are 4 by 4. So we have some base cases. First of all, what if we go out of bounds? How are we going to go out of bounds in this case? Because our row is never going to be too small, because we're starting here, but we can only move down. So if we go out of bounds, it's because we went too far out, not because we went too far up. So when we reach this case, it'll be because our row is equal to 4, which is the number of rows we have. So if r is equal to 4, then we went out of bounds. Same thing with the column. We can only move to the right. We can't move to the left, so that simplifies things for us. So when we go too far to the right, so if c equals the number of columns, we can return 0. That basically means we went out of bounds. There's no valid path that goes out of bounds that reaches the result. The other base case, of course, would be if, we did reach the goal. So that would be if r is equal to rows minus 1 and column is equal to columns minus 1. In that case, we would return 1. That means, okay, this is a path. Otherwise, suppose we're actually starting from here. It's not a base case. So what we would do is call brute force 2 times, because we can either go down, that's this first case where we say row plus 1, or we can move to the right where we say column plus 1. So brute force, this is going to basically be a decision tree with 2 branches, because for every position, no matter where we're at pretty much, we can either go down or to the right. We can't go in 4 directions. We can only go, in 2 directions. So this decision tree has 2 branches. What's the height of the decision tree going to be? Well, like I said, every path is going to have the same length. So any path in our decision tree is going to have the same height, roughly. And the height is basically going to be the number of rows plus the number of columns, because that's practically what the length of every single path to the destination is going to be. So we can say that the time complexity is 2 to the power of n plus m, where let's say these are the dimensions of the grid. So I've written that up here as well. So that's the time complexity. So obviously it's not very efficient, but we can make it much more efficient. Basically, the time complexity can be reduced to the size of the grid, because we're going to notice some repeated work. First, I'm going to quickly walk through a little bit of the brute force, and then we're going to see how we can use caching to improve the time complexity. So first we start here, we go down and we go to the right. So now we want to know how many ways can we reach the destination from here and from here. Well, from here, we're again going to go to the right, or we're going to go down, or we're going to go to the right. From here, we're going to do the same thing, go down or to the right. And then, from here, suppose we're going to go down and to the right, and then from here we're going to go down, which is a base case, that's going to return 0, and we're going to go to the right over here. From here we're going to go down, can't do that, we're going to go to the right as well. From here, same thing, but finally we get to the destination. This is going to return 1 for us. So when we're calculating how many ways from here can we reach the destination, we're going to have a value of 1 now. What about from here? Well, here was 0 because we went out of bounds, but from here was 1. So we're going to take those two results, add them together, and we get a 1 over here. Same thing for this guy. There was a 0 here and a 1 here. So add them together, we get a 1. Now, finally, when we get back up over here, we have the value below, but now we're trying to calculate the value that's over here. Well, from here, we can have two choices. Go to the right or go down. We have the value down here, but what's the value over here? We don't know. We have to go down and we have to go to the right. Well, what about from over here? Again, we can go down and to the right. Well, right is out of bounds. That's going to return 0. Down is reaching the destination. That's going to return 1. So add those together, we get a 1 over here. Now we can calculate what goes over here. 1 plus 1. So add those together, we get a 2 over here. What about in this position? There's a 1 over here and there's a 2 over here. Add those together, we get a 3 in this position. Then we can calculate what goes over here. 1 plus 3, add those together, we get a 4 in this position. So now you're starting to get the idea. So as we try to calculate, starting from here, how many ways can we reach the destination, we pretty much have to we have to solve the sub-problem for every other position, because to solve this problem over here, we have to solve these two problems. But to solve these two problems, then we have to solve these next three problems. And to solve those, we have to solve these, and etc., etc. We have to keep going until we get to the base case, which is the result, and then work our way back to what we were originally trying to do. When you do this recursively and then add caching to it, which I'm going to go over right now, this is called the top-down dynamic programming approach. But as you might have noticed, we can eventually also work our way starting from the bottom and then work our way up, which is going to be the true dynamic programming approach, which is called the bottom-up approach. But for now, let's focus on taking this brute force and adding caching to it. So let's undo a little bit of this work and go back to some of the basics that we were talking about over here. For every single position, no matter what it is, we can get how many ways from here can we reach the result just by taking the value below it and the value to the right and adding those two sub-problems together and then assigning it over here. But notice something. If we want to solve this sub-problem, we have to solve this sub-problem and this sub-problem. But if we want to solve this subproblem, we have to solve this subproblem and this subproblem. Well, we have to solve this subproblem twice. That's where the repeated work is coming in. And it's going to get worse and worse. From here, we have to solve this and this. From here, we have to solve this and this. From here, we have to solve this and this. This is being done twice, as you can see. This is being done twice, as you can see. So there's a lot of repeated work going on, and I could draw out the entire thing. I encourage you to do that if you want to have a better understanding of it. But the idea is there's going to be a bunch of cells that have repeated work. And it's going to be exponential because you can see that there are two different ways that we can land in this spot. That means there's going to be two different ways we can go move to the right over here. There's two different ways we can land in this spot. So there's going to be two arrows actually going down here, two arrows going to the right. So it's going to get more and more and more. And if we had a really big grid, it would be very, very inefficient. So caching is going to help us a lot here. So in terms of code, the good thing is about caching, there's very few changes that you actually have to make here. So essentially the first base case is going to stay the same, and the second base case is going to stay the same, but in between that, we're going to add the case where if our cache, which in this case is a two-dimensional array, which is going to be the exact same size as our input grid. Well, technically we don't have a grid, but the cache is going to be of the dimensions of that, input. And you could also use a hash map if you wanted to. Generally, I prefer to use a hash map, but in this case, we're using a two-dimensional grid, and our memoization solution has an extra parameter for that two-dimensional grid cache that our brute force did not have. And when I'm passing in a grid here, this is kind of complicated. If you're not familiar with Python, this is essentially creating a two-dimensional grid with all zeros. That's a 4x4 essentially. If you are familiar with Python, you still might not understand this because this is, kind of a weird syntax. essentially we have an array of size 1 with a 0 inside of it. We multiply it by 4, which gives us an array of size 4 with 4 zeros inside of it. And then we create a outer array, taking that array and creating 4 copies of it. That's where this comes from. And that gives us basically a 4 by 4 grid with all zeros inside of it. It's a lot easier to do this in most other languages, thankfully. But when we have that cache, if we don't go out of bounds, so take this, for example, we went down and to the right, and then from there we went down and to the right, and then from here we went down and to the right. But in reality, one of these is going to execute first. Let's say this one executes first, and then we calculate how many ways from this position we can reach the result. And once we have that, we're going to add it to our cache. So you can think of this grid as being our cache. We're going to put the value here. So as we saw before, all the values in the bottom row are going to be 1. That makes sense because from here, we can't move down. We can only move to the right. So from here, there's one path that can lead us to the result. And from here, there's one path that can lead us to the result. From here, there's one path that can lead us to the result. The next row we already filled out earlier looked like this. So now let's briefly go over filling out the rest of it. So from here, we want to calculate the value. We go down and to the right. We don't have the value here. Let's go down and to the right. We don't have the value here. Let's go down and to the right. There's nothing on the right, but below there's a 1. So here we can put a 1 as the result. Now we can calculate the value that goes here. 2 plus 1, that's going to be 3. Now we can calculate the value that goes here. 3 plus 3 is 6. And we can calculate the value that goes here. 4 plus 6 is 10. So now when this guy wants to go down and to the right to calculate the value that goes here, we already have the value that goes here. We cached it. By building this grid, we added it to our cache. We're not going to run DFS. We're not going to run, our recursive call from this position again and do all that repeated work. We don't have to do that anymore. So from here, when we go down, we're going to check, is that value out of bounds? Nope. Is that value in our cache? Yes. So we can return that value in our cache, which is 6, but we still have to calculate the value that goes over here. By the way, the order of this is somewhat important. Now, these two could be swapped. You don't have to put them in this order, but it is important that we put this before this because we have to check if we went out of bounds before we try to index this two-dimensional array. Because if we index it with, an R or a C that's out of bounds, then we're going to get an exception thrown or an error or something like that. So this is usually the first check that you want to make. You want to make sure we're not out of bounds. That's really important. But otherwise, if none of the base cases execute, we're basically running the same thing we did with our brute force. We're running the recursive call, going in both directions, either R plus 1 or C plus 1, passing in the same, hard-coded values, rows, columns, whatever, and passing in that cache, which is a reference to the object. We're not creating a new cache every time we call the recursive function. We're only creating a single cache initially and then reusing that throughout the recursive calls. And then when we add the result of those two together, so in this case, we're going to recursively call memoization over here. We're going to go down and to the right. And from here, we're going to go down and to the right. This is going to be a 0. There's a 1 over here. Add those together. We get a 1 here. What value goes here? 3 plus 1. So we get a 4 over here. Now we can finally calculate what goes over here. It's 6 plus 4. So there's 10 ways from here that we can get to the destination. There's 10 ways from here that we can get to the destination. Add those two together. That means there's 20 different ways from the starting point that we can get to the destination. And these are all unique paths. So this is something how it would play out if we did it recursively with memoization. But as you kind of saw, why should we even start at the top and work our way down and then recursively, solve the subproblems and then go back up? Why not just immediately start at the bottom and then fill in these values and then get all the way to the top and ultimately have that result anyway? Well, the time complexity will still be the same because we still have to pretty much fill out this entire grid. As you saw right now, the time complexity is the size of the grid. We're not doing any repeated work, but in this case, we also have to declare a bunch of space. We have to create a two-dimensional grid, which is going to be the same size. But the benefit of dynamic programming is sometimes we don't have to declare all that extra space. As we saw with the Fibonacci sequence, we were able to save space by using the bottom-up approach. The same is true with this problem. Let me show you what I mean. So this is what the code for the true dynamic programming, aka bottom-up approach, would look like. It's usually pretty short for dynamic programming problems. The bottom-up approach usually has a lot less code than the recursive approach, but it's usually difficult to come up with unless you have a good understanding of the recursive approaches. And there are many dynamic programming problems that follow this same pattern of having a two-dimensional grid and, solving sub-problems that are below and to the right, and then eventually arriving at the solution. So in this problem, what we're going to do is start bottom up. We're going to start at the base case and then calculate these values and then go here and then calculate these values and then keep going like that. Now, it's intentional, the order that we're solving these subproblems, and we kind of have to do it this way, starting at the last row, going to the left, starting at the next row, going to the left, because, well, this is the base case, and for us to know this value, we have to get the bottom value. Good thing here is for the last row, there's nothing below. We can just kind of assume that there's a bunch of zeros here if we really want to. And that's sometimes a technique that's used in more complicated two-dimensional dynamic programming problems. In this case, we'll look below, that'll be 0, and we'll look to the right, and what we expect from here is that there's a 1 there. Now, it doesn't really make sense that from here, how many paths are there that can lead to this position? Well, is there 1 path or is there 0 paths? Technically, to me, it makes sense that there would be 0 paths, but as the base case, we put a 1 here because that's just what allows our math to work out. If we put a 0 here, then the value we're going to get here is going to be 0, and then here, and then here, and then all of these are going to end up being 0. We know that's not correct, so we put a 1 here. And then when we want to calculate this value, we go below and to the right, we take this, add it, and then we get a 1 here. And so we have to compute it like this. And then when we want to get to the next row, we already have all of these populated. So for us to calculate this position, we look below and to the right, there's nothing there. And we already have the value populated here. So we'd get a 1 here. And then we can populate this value only after we've gotten these two. We can add them together and get a 2 here. So it's going mostly in the same order that our recursive algorithm did and the memoization one did. It's just we're immediately starting at the bottom and working our way up. We're not even making the recursive calls starting from the top. So in terms of code, it would basically be the exact same thing. What we're going to do here is declare a previous row, which is going to be all zeros. What that basically is, we're implicitly creating a row over here that's just telling us that there's all zeros over here. And then we're iterating through this 2D grid, starting here, starting in the last row and then going up and up and up. And in our nested loop, we're starting at the last column and then working our way to the left. Well, technically, we're not starting at the last column. We're starting at column minus 2, the number of columns, which in this case would be 4. That's what we're passing in here, 4 minus 2. So we're starting at the second to last column. Why am I doing that? Well, because we know that the base case is going to be 1 anyway. So we actually fill in that base case. We create a current row. So this is going to be our current row, and we're going to fill in a 1 at the last position. And we actually know that for every row, the last value is going to be 1 because we know from any of these going down, there's only one way to reach the destination. We can't go to the right for any of these anyway. But notice how we're actually not creating a 2D grid because it's not necessary. Notice how to fill in this entire row, all we need is the previous row, aka the row below it. And that's enough. We don't need anything from the row above or the row above that. We just need the row below it. And to get the values in this row, we only need the values below that row. So at any given point, we're only going to have 2 rows in memory, the previous row and the current row. So the space complexity is going to be 2 times the number of columns. Let's say m is the number of columns. So this is the space complexity. This can be reduced, of course, to big O of m, because we don't care about constants. So that's the space complexity of this approach. Clearly, the time complexity, we are having to still iterate through the entire grid. So the time complexity is still going to be n times m. And if you're a little bit confused by the syntax that we're doing here, this is Python. Of course, you could do this in any language. But this is basically starting at rows minus 1, and this is starting at columns minus 2, this column. And this is basically saying we're going to keep going until we've gotten to the 0th row, and we're going to stop as we get to the -1 row. So we're not going to execute when we get to the -1 row, and we're not going to execute when we get to the -1 column position. That's why we have -1 here as well. And the last -1 basically means we're decrementing each time. So we're going to take the column, decrement it each time. In most languages, I think it's a little bit more obvious what the for loops are doing, and we have the code for those below if you want to check them out. So at this point, you probably get the idea, and I bet you could fill in this grid yourself if you really wanted to, but I'll do it really quickly. So when we want to calculate the value here, which is current row, we're going to take the current row column plus 1. So that's our way of looking to the right. We take the current row and get the column plus 1. To get the value below, we take the previous row in the same column. So we take those, add them together, and then assign that value here. It's going to be 1. We're going to do the same thing here and here. They're all going to be 1. Now, before we start looking at this row, we're going to take our current row, which was this, and assign it to previous row. So this is now going to be considered our previous row. This is no longer going to be in memory. And now here, we're going to create a new current row of the same dimensions. It's going to initially be all zeros, but we're not going to care about that. And the last value here is going to be a 1. And then we're going to start calculating these. This one is going to be 1 plus 1, 2. This one is going to be 3. This one is going to be 4. And then we're going to do the exact same thing over here. This is going to be out of memory. This is going to be the new previous row. And this is going to be the new current row. There's going to be a 1 here. This is going to get a 3. This is going to get a 6. This is going to get a 10. And again, this is going to be removed from memory. This is going to be the new previous row, and this is going to be the new current row. There's going to be a 1 here. This is going to be 4. This is going to be 10. This is going to be 20. And then finally, we're going to delete this from memory as well. This is going to be our previous row. We're going to return the 0th value in that previous row. That's exactly what we wanted. We're going to return the 20. So this is, believe it or not, a relatively simple two-dimensional dynamic programming problems. They can get a lot harder, but if you can get really good with the concepts that we talked about here, understanding the idea of decisions that we're making, not doing any repeated work, and basically filling in the values of a grid, you can go very, very far with more difficult dynamic programming problems. If you want to practice some, check out the practice section and look at the problems in the two-dimensional dynamic programming topic.